Okay, so hello everyone. In this video, we will cover solution for popular race condition using binary semaphore. First, we will discuss producer-consumer problem solution. Then we will see reader-writer's problem, and then at last we will discuss very popular and important problem, dining philosopher problem. It has been asked before in the GATE exams also, so it is very important also. Now, moving forward to producer-consumer problem solution. So let's see the solution of producer-consumer problem. What is the producer-consumer problem? What causes the producer-consumer problem? And what are the flows in it? We have discussed it in our previous videos, so you can check it out that. But for your understanding, I can clarify here also that the producer consumer problem occurs when we have producers that create data and consumers that consume data from a shared buffer. This creates inconsistency or data loss problem when processes run simultaneously without proper synchronization. So here we are solving the producer consumer problem by using binary semaphores as well as counting semaphores to achieve synchronization. We have taken two counting semaphores, full and empty. Empty tells us the number of empty slots in the buffer where producer puts the data and consumer consume items, and full tells us the number of filled slots, how many slots are already filled with the data. We also have one binary semaphore S initialized to 1. The producer code is entry code is down empty, down S, and critical section is buffer in is equal to item and in is equal to in plus 1 mod n. This was the critical section in producer consumer problem where it is causing the problem. And what is the exit code? Up S, up full. Now let's solve this step by step. Case 1 is sequential execution without preemption. Let's say at this point in time we already have three values in slots 0, 1, 2. There are three items A, B, C already placed. So if we talk about empty first, the value of empty here is 5 because what is empty? Number of empty slots. How many total slots do we have in the buffer? 8. Out of those 8, 3 slots are filled. So how many empty? 5. And full means number of filled slots. How many slots are it already filled? We have 3. So at this point in time my empty is 5 and full is 3. Now when producer comes, producer want to produce one item. So what will it do first? To produce an item, it does down empty, and down empty means it wants to use one empty slot because it will put one item in it. So to use one empty slot, it will first do down empty, making the value is 4. Then the second instruction is down S, and down S means the binary semaphore value is made from 0 or 1. Since S was initialized to 1, it successfully makes the value of this one be 0. So value will become 0, which means it enters the critical section where we are actually executing the code. Next, it puts item D in buffer in, and in is pointing at the third location because in shows the address of that empty slot, like where we can put that data. So the value of in is 3. Now we put item D in the third position and update in is equal to in plus 1 mod n. The value of in was 3, so 3 plus 1 mod 8 is equal to 4 mod 8 is equal to 4. We update in value from 3 to 4. After this code is executed, we have exit section code. When it exits the critical section, it execute up S, making the semaphore value from 0 to 1 again. Why? Because we are giving chance to other process to execute their code for progress. Now then up full, like up full makes the value of full 4. Now meaning we now have 4 slots filled. To check consistency, how many empty slots? 4. How many full? 4. So 4 plus 4 is equal to 8, and we have 8 total slots. So now consumer comes, consumer want to consume one item from this buffer. First it execute entry section code, down full and down S. Full has value of 4, so we make it 3. Down S converts semaphore value from 1 to 0. Then it enters critical section. Now buffer out. What is out value? Out value is 0. So the pointer is pointing to position 0. The item there is which we consume and put in variable items. Out is equal to out plus 1 mod n. The value of out which was 0 gets incremented to 1. Now the up S makes semaphore value 1 again. So if producer want to come again, we create scope for it. Now up empty means one empty slot increase. So we increment the value from 4 to 5. Now we can verify empty is 5, full is 3, as we can see it on the screen also. So 5 plus 3 equals to 8 slots here. We have 3 filled slots and 5 empty slots. This producer consumer code works properly when we execute sequentially. Now we are looking at case number 2. What is case number 2? A concurrent execution with preemption. Now let's check one more example where we try preemption, because the major problem comes when process execute concurrently. When they execute at the same time, it becomes very important to synchronize them. Let's start again with the empty value 5 and full value 3. producer comes and execute down empty, making empty value from 5 to 4. When it was about to do down S, the producer becomes preempted and consumer enters. Consumer comes and does down full, making full value from 3 to 2, then down S makes semaphore value from 1 to 0. So consumer enter critical section. The key point is down S, whichever process, producer or consumer, first does down S will enter critical section first and the other cannot come. So consumer enters critical section, item is equal to buffer out. So picks item from location 0 and puts it in the item variable. So out is equal to what? Out is equal to out plus 1, update out from 0 to 1. Now let's see if consumer is at this point, can producer come? This was the problem in producer consumer problem. When one process is running and other processor comes at the same time, it could create inconsistency. But here we stop this. Consumer is running, but if system gets preempted again and producer tries to resume, producer has already executed the first line making empty from 5 to 4, but can it do down S? No, because S value is already 0. Since semaphore value is 0, when producer tries down S, the producer will be blocked. Now that's what we are doing here. If one process is running and another comes, the second one gets blocked, so it can execute further. This prevents the producer consumer inconsistency problem. Now consumer continues execution. Up S makes the S value from 0 to 1, up empty, update empty value from 4 to 5. Now consumer is fully executed. Now control comes back to the producer. In producer's PCB process control block, it saved that it executed instruction 1. So execution start from the instruction 2. Down S, it makes the S value from 1 to 0 successfully. Buffer in is equal to item and item D gets plates at position 3 and in is equal to in plus 1 makes in value 4. Producer continues. Up S makes S from 0 to 1 during exit and up full makes full value to from 2 to 3. Now final verification is what? Empty value is 5, full value is 3, as we can see on the screen also. Now total is 8. Consumer consumed one item A and from location 0 and out is updated to 1. We have 3 field slot and 5 empty slot. This is how the producer consumer problem works, and this is the solution using binary semaphore and counting semaphore. You can also try solving this using mutex or locking methods. Now moving forward to reader writers problem. We are going to discuss the reader writers problem, a standard synchronization problem in the operating system. Before discussing the problem, let me explain the base scenario. We have a database, a collection of related data. Two types of user access this database, readers and writers. Readers only want to view the data and read it. Writer want to update something in the data. For example, on IRCTC Indian Railway website, if we check train status by entering a train number, that's just reading data. We are viewing information without modifying anything. But if someone is reserving tickets, that's a write operation because we are making changes to the ticket count. So we have two users, readers and writers. The problem is that multiple users can use the database simultaneously. If they are using it at the same time, what problems can occur? The problem scenarios are if one reader is already using data and a writer comes to the same data, this creates a problem. If writer is already using database and reader comes, this also creates a problem. If writer is updating the database and another writer comes to update the same data, this creates a problem. If one reader is reading the data and another reader comes, this is not a problem. This does not create any problem. Remember, we are talking in same data. Okay, so the important constraint here is same data. If a reader works on the data A and writer works on data B, that's no problem because they are operating on different data. We are talking about the same data, like creating read write, write read, write problems. These are standard problem in DBMS transaction control and concurrency, but read doesn't create any problem. If these problems occur in the database, big issues arise because data can be lost or inconsistency is created. To prevent this, we need to synchronize these processes, readers and writers. For synchronization, we have methods like semaphores, monitors, locks, but semaphore is the most popular method. I want to write code such that the 3 problematic cases don't occur, but if 2 or more reader want to come simultaneously, they can. Not just 1 or 2, even 100, even 1000, even 1 lakh readers can come with no problem. Now my code should prevent the 3 problematic cases but allow multiple readers in any time. Now solution code using semaphores. This code uses int rc is equal to 0, meaning read count is what? Number of readers in the database. Now second is 2 semaphores, mutex and db, both initialized to 1. And what is the reader code? While true means this condition will always be true. Down mutex, rc is equal to rc plus 1 means a reader comes, then a reader count will be 1, and then if rc is equal to 1, then down db, and up mutex. Okay, so this is what? This is entry section code. code, and we have the critical section accessing database after this code. And what is the exit section code? Down mutex rc is equal to rc minus 1. If rc is equal to 0, then up db and up mutex. So this is the code for reader's code. Now what is the writer's code? Writer's code is while true, down db, this is entry section code, down db, and then critical section, and then critical section accessing database, and then we have the exit code up db. This is what writer's code. When writer comes, it will execute this code, and when reader comes, it will execute this code. For reader, the first part is entry code to enter critical section. Database access is the critical section where common resources database is accessed, and the last part is exit code. Now what is case 1? Case 1 is read write problem. Let's say reader r1 comes first, initialize value rc is equal to 0, mutex is equal to 1, and db is equal to 1. Now when r1 comes, while true is always true, now down mutex makes mutex value from 1 to 0. Now rc is equal to rc plus 1. Read count increases from 0 to 1. One reader comes, so it will be 1. If rc is equal to 1, yes, 1 is equal to 1, it is true. So down db makes db value 1 to 0. Up mutex means makes value from 0 to 1. r1 happily enters database and starts reading. Now let's say a writer comes at the same time wanting to use the same database. Writer runs. Now while true is always true, now down db want to make db value from 1 to 0, but db value is already 0. Since db is already 0, it cannot be reduced below 0. Binary semaphore. So the writer process gets blocked. The writer is blocked and cannot enter critical section. This establishes our first case. If a reader is already reading, a writer cannot come. Now case 2 is what? Write read problem. Now we will see that writer w1 comes first. While true is always true, down db makes db value from 1 to 0. w1 enters the database successfully. Now when reader r wants to come, while true is always true, down mutex make mutex value from 1 to 0. It is successful. Now rc is equal to rc plus 1. This line will also execute. Read count becomes 1. If rc is equal to 1, 1 is equal to 1, this is true. So down db. So it will down db, but db value is what? It is already 0. So reader cannot make db value from down from 0 to minus 1, because it is binary semaphore. We have read that only two values are there, 1 and 0. So reader will be blocked on this line. Case 2 is also satisfied. We have satisfied and we have established this case. If a writer is already in database, reader cannot come. Now what is case 3? Write problem. Writer w1 comes. Down db, it will make down db makes db value from 1 to 0. w1 enters the database. Now writer w2 also want to come. So while true is always true, down db value is 0, cannot be made like minus 1. So w2 is blocked because we have entered the w1 and it makes db value 0. So db value cannot be made from minus 1 because it is binary semaphore. So case 3 is also established. We have blocked the w2 also. So if one writer is writing, another writer cannot write the same data. Now case 4, read problem. There is no problem. Reader r1 comes, down mutex becomes 0, rc is equal to rc plus 1, rc becomes 1. If rc is equal to 1, this is true. So down db becomes 0. Up mutex become like 1, and r1 enters the database. So this is what r1 enters. Now if reader r2 wants to come, then it will allow, but how? Down mutex value is 1, so it becomes 0. rc is equal to rc plus 1. Read count becomes 2. What is the third line? If rc is equal to 1, but rc is now what? rc is 2. So this line will not execute. So up mutex now makes value from 0 to 1. So r2 also enters the database. So this is how the reader always enter the critical section. Our case 4 works properly. Both readers can access database simultaneously. Even r3 can come. It will make rc is equal to 3. Condition fails and r3 enters. All readers can enter easily. Now what is the exit process? When r1 finishes and want to exit, down mutex from 1 to 0. rc is equal to rc minus 1 reduces reader count from 3 to 2. Now if rc is equal to 0, 2 is equal to not 0, then it is false. So up db doesn't execute. This line will not execute. Now up mutex from 0 to 1, so it will execute. Now the beauty is in this logic. If rc is still 2, meaning 2 readers are still in the database, don't up the database value. If we make db value 1, writer would get opportunity to enter, which we don't want to like while reader are already inside, we don't want to writer to come. So when r2 exits, same process, rc becomes 1, condition is still false, db stays 0. When r3 last reader exits, down mutex becomes 0, rc minus 1, rc becomes 0, so no reader inside. If rc is equal to 0, this condition is true. true, so up db becomes 1, up mutex becomes 1. Now writers can come because db value is 1. This ensures that writers only get actions when all readers have finished. The up mutex is like in the exit code allow new readers to enter even while others are reading. This maintains the ability for multiple readers while properly controlling writer access. So this is reader writer problem and its solution. Now moving forward to dining philosophers problem, a very important problem. The dining philosopher problem is a standard operating system problem like producer consumer problem and reader writer also. Let's first discuss what the problem states. We have a dining table with 5 philosophers sitting around it. P0, P1, P2, P3, P4. There are 5 folks, F0, F1, F2, F3, F4. These folks are need to eat from the rice bowl is in the center. At many places you may see a chopstick instead of forks. Focus on the concept, not the specific food item. Now in this code, every philosopher has 2 states, thinking and eating. Philosopher's job is to think, but when they get tired of thinking and feel hungry, they start eating. For eating, we have designed a code that every philosopher follows. When a philosopher finishes thinking, it will take the ayat fork, left fork, and take the right fork and start eating, and then will finish eating and then put down the right fork, put down the left fork, and then the code exists. Now case first is sequential execution. Let's say P0 comes first, P0 wants to eat, so it follows the code. Take ith fork, I is equal to 0, so take F0, left fork of P0. Take right fork, 0 plus 1, so take F1, start eating, put down F0, then put down F1. This is the sequential execution. Now P1 comes next, take fork number 1 and F1 and left of P1. Second fork, 1 plus 1 mod 5 is equal to 2, so F2, right of P1. Eat and then put down F1 and then F2. If philosopher come sequentially, this code works perfectly with no problems. But in case 2, concurrent execution problems. Let's say P0 comes and picks up fork F0, left fork, but before picking the right fork F1, P1 comes. P1 picks the F1, its left fork. Now P0 is waiting for F1, which P1 has, creating potential race conditions. To solve this, we use semaphore, especially binary semaphores. Solution using binary semaphores. We use an array of 5 binary semaphores, S0, S1, S2, S3, S4, corresponding to forks F0, F1, F2, F3, F4. All semaphores are initialized to 1. Now, modified philosopher call is what? Wait Si. Now Si is array here. Si means we have taken the semaphore. Now take left fork Si here. Wait Si plus 1 mod n. Take right fork. This is the entry code, and the eat section is critical section, and the exit section is what? Signal Si, signal Si plus 1 mod n. Now I have told you also that we can call it wait P also, we can call it P, we can call it down also, and we can call signal the V operation, or we can call up operation also. So this is the terms, but here we are using wait and signals. So this is what? This is modified philosopher code. Each philosopher needs 2 semaphores to eat. P0 needs S0 and S1, P1 needs S1 and S2, P2 needs S2 and S3, P3 needs S3 and S4, P4 needs S4 and S0. Now, multiple philosophers can eat simultaneously if they are independent. For example, P0 using F0 and F1 and P2 using F2 and F3. They can eat together since they use different forks. This is a special case where more than one process can be in the critical section simultaneously, but they must be independent. If you look at the table, P0 and P2 are opposite. Each other can use completely different forks, so both can eat from the rice ball. Similar, P1 and P3 can eat together, or P4 and P2 can eat together as long as their required forks don't overlap. The most important case is the deadlock scenario. Let's say all 5 philosophers come simultaneously. All semaphore starts at 1, like we have initialized to 1. Each philosopher execute their first instruction. P0 wait S0 and makes S0 from 1 to 0. It picks F0, but before picking up F1, P1 comes. Now P1 wait S1, it makes S1 from 1 to 0. Now it picks the F1. Now before picking up the F2, P2 comes and wait S2, and it makes the S2 from 1 to 0. Now it will pick the F2. P3 will pick the F3, and P4 will pick the F4. But before executing their second instruction, taking right fork, they all get preempted. Now all semaphore values are 0. When they try to continue, P0 needs S1 for right fork, but S1 is equal to 0 held by P1, it is blocked. P1 needs to S2 for right fork, but S2 is equal to 0 held by P2, it is blocked. P2 needs S3 for right fork, but S3 is equal to 0 held by P3, it is blocked also. P3 need S4 for right fork, but S4 is equal to 0 held by P4, so it is blocked. P4 need S4 for right fork, but S0 is equal to 0 held by P0, blocked. It is also blocked. So this creates a circular wait situation. Everyone holds one resource but need another that's held by someone else. This is deadlock because all philosophers are blocked and no one can proceed. So deadlock prevention solution. What is the solution for this? To remove deadlock, we modify one philosopher behavior. Instead of all philosopher picking left fork and first and then right fork, we make the last philosopher P4 pick the right fork first then left fork. So for P4, the modified code becomes wait S0, wait S4, and then critical section it, then signal S0, signal S4. This is what this is P4 will execute. P4 will take the right fork first and then it will take left fork. It will not create a deadlock. Now when all philosophers try to start, P0 to P3 pick their left forks, S0 to S3 became 0. Now P4 tries to pick the right fork first, S0, but S0 is already 0. P4 gets blocked. Now since P4 is blocked, S4 remains 1. P3 which holds S3 and needs S4 for its right fork can now proceed. P3 gets S4, it eats, then releases S3 and S4, both became 1. Now P2 can then get S3, eat, and it releases S2 and S3. Now P1 can get S2, now it will eat and release S1 and S2. P0 can get S1 and it will now eat and release S0 and S1. Now finally P4 get unlocked, gets S0 then S4 and eats. So this is how we prevent the deadlock situation. This asymmetric approach breaks the circulation wait condition. You don't have to reverse only the last philosopher. You can modify any of one philosopher. For n philosopher, n minus 1 follow the normal sequence left then right, and 1 follows the reverse sequence right then left. So this solution ensures deadlock free execution. So this is all about these problems. These are very popular problems and can be asked in your exams, so prepare accordingly. So that's it for this video. We will meet in next video. Until then, bye bye. बहुत लंबा हो गया नहीं ये वीडियो.